Let us discuss one more new topic today. It's not a new topic, actually the same thing we are continuing. Of course, it's actually a new topic also. It's about black body radiation, and we are following the same pattern. We shall briefly discuss what is black body radiation, and again we shall briefly discuss what is the distribution of energy in the black body spectrum, and later we shall try to discuss why classical theories fail to explain the distribution of energy in the black body spectrum or black body radiation. And then of course, since the classical theories fail to give proper explanation, there should be a proper explanation on the basis of quantum theory. And the discussion based on quantum theory is also we are discussing. BMW. Okay. Let us discuss about black body radiation. Can somebody say what is a black body radiation?
The body which absorbs all the radiation falling on it.
Yes, a body, an object which has the capacity of absorbing all the radiation that is falling on it, covering a wide range of wavelength. Okay, when we speak of radiation falling on the body, please remember radiation means electromagnetic radiation. If you say electromagnetic radiation, there is a range of frequency or there is a range of wavelength. So therefore, we expect, so irrespective of the wavelength, or you can also say in terms of frequency, irrespective of the frequency, so a black body would absorb all the radiation that is incident. Okay, for any wavelength. ಯಾವ wavelength ಆದ್ರೂ ಸರಿ ಅದ್ರ ಮೇಲೆ ಬಿದ್ದಿರೋ ರೇಡಿಯೇಷನ್ ನ ಎಲ್ಲಾ ವೇವ್ಲೆಂತ್ ಅಲ್ಲೂ ಕೂಡ ಪರ್ಫೆಕ್ಟ್ ಆಗಿ ಕಂಪ್ಲೀಟ್ ಆಗಿ ಅಬ್ಸರ್ವ್ ಮಾಡ್ಕೊಳ್ಳುತ್ತೆ ವಿತೌಟ್ ರಿಫ್ಲೆಕ್ಷನ್ ವಿತೌಟ್ ಟ್ರಾನ್ಸ್ಮಿಷನ್. ಪ್ಲೀಸ್ ರಿಮೆಂಬರ್, ಅಬ್ಸರ್ವ್ ಮಾಡ್ಕೊಳ್ಳೋದು ಅಂತಂದ್ರೆ ಅರ್ಥ ರಿಫ್ಲೆಕ್ಟಿವ್ ಮಾಡಬಾರ್ದು, ಟ್ರಾನ್ಸ್ಮಿಷನ್ ಮಾಡಬಾರ್ದು, ಎಲ್ಲ ಹೀರ್ಕೋಬೇಕು, ಒಳಗಡೆನೆ ಸ್ಟೋರ್ ಮಾಡಿ ಇಟ್ಕೋಬೇಕು. Okay, such an object is what we call it as a perfect black body. Okay, and it is not like that it would only observe the energy. Black body ಯಾವಾಗಲೂ ಕೂಡ ಎನರ್ಜಿನ ಅಬ್ಸರ್ವ್ ಮಾಡ್ಕೊಳ್ಳುತ್ತೆ ಅಂತ ಅನ್ಕೋಬೇಡಿ. Okay, so if you heat black body to a high temperature, then it would emit radiation of the same wavelengths or the same frequency that it absorbs at low temperature. Low temperature ನಲ್ಲಿ ಇಟ್ಟಾಗ ಯಾವ ವೇವ್ಲೆಂತ್ ರೇಡಿಯೇಷನ್ ನ ಅಬ್ಸರ್ವ್ ಮಾಡ್ಕೊಳ್ಳುತ್ತೋ ಸೇಮ್ ವೇವ್ಲೆಂತ್ ರೇಡಿಯೇಷನ್ ನ ಏನ್ ಮಾಡುತ್ತೆ, ಎಮಿಟ್ ಮಾಡುತ್ತೆ. ಯಾವಾಗ? when the black body is maintained at a high temperature. ಆ ಬ್ಲಾಕ್ ಬಾಡಿನ ನೀವು ಲೋ ಟೆಂಪರೇಚರ್ ನಲ್ಲಿ ಮೇಂಟೈನ್ ಮಾಡಿದ್ರೆ ಅದ್ರ ಮೇಲೆ ರೇಡಿಯೇಷನ್ ಇನ್ಸಿಡೆಂಟ್ ಮಾಡಿದ್ರೆ ಎಲ್ಲದನ್ನು ಅಬ್ಸರ್ವ್ ಮಾಡ್ಕೊಂಡ್ಬಿಡುತ್ತೆ. ಅದೇ ಬ್ಲಾಕ್ ಬಾಡಿನ ನೀವು ಲೋ ಟೆಂಪರೇಚರ್ ಮೇಂಟೈನ್ ಮಾಡಿದ್ರೆ, ಅಂದ್ರೆ ಲೋ ಟೆಂಪರೇಚರ್ ಇನ್ ದ ಸೆನ್ಸ್ ಸರೌಂಡಿಂಗ್ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ, ಹೈ ಟೆಂಪರೇಚರ್ ನಲ್ಲಿ ಮೇಂಟೈನ್ ಮಾಡಿದ್ರೆ, then in the respective case it emits the radiation. Okay, so please remember, a black body is a perfect observer of radiation at low temperature. It is also a perfect emitter of radiation at high temperature. Okay, so therefore the radiations which are emitted by a black body when it is maintained at a high temperature is what we call it as black body radiation or black body radiation or radiations, whatever you want to call. Okay, the better word is radiations, because the radiation would be consisting of different components having different wavelengths. Okay, ಬೇರೆ component ಇರುತ್ತೆ, ಒಂದೊಂದು component ಒಂದೊಂದು wavelength ಇರುತ್ತೆ, ಹಾಗಾಗಿ radiations ಅಂತಾರೆ word use ಮಾಡ್ಕೊಳ್ಳಿ. Okay, so therefore I can say that the emitted radiations by a black body are called black body radiations. Okay, ಅದು radiation emit ಮಾಡ್ತಾ ಇದೆ ಅಂದ್ರೆ ಅರ್ಥ ಏನು? energy emit ಮಾಡ್ತಾ ಇದೆ. So therefore there is a distribution of energy among the different components of black body radiation. Okay, black body ಇಂದ ಬರ್ತಿರೋ ರೇಡಿಯೇಷನ್ ಬೇರೆ ಕಂಪೋನೆಂಟ್ ಇರುತ್ತಲ್ಲ, ಪ್ರತಿಯೊಂದು ಕಂಪೋನೆಂಟ್ಗೂ ಒಂದೊಂದು ಎನರ್ಜಿ ಇರುತ್ತೆ. Okay, so this arrangement of intensity of the radiation, of the radiation over a wide range of frequencies, wide range of wavelengths is what we call it as black body spectrum. Okay, so please concentrate here. So this is what we call it as black body spectrum. So I can simply say that arrangement of energy over a wide range of frequency or wide range of wavelength is what we call it as black body spectrum. Okay, and this is what the black body spectrum that we are discussing here. So our main or the center object, okay, for our discussion is distribution of energy in the black body spectrum. Simply we call it as black body spectrum. Black body spectrum ಒಳಗಡೆ ಎನರ್ಜಿ ಬೇರೆ ಬೇರೆ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಹೇಗೆ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಆಗಿದೆ ಅನ್ನೋದು ಡಿಸ್ಕಸ್ ಮಾಡಬೇಕು. Okay, that is what the core point of our discussion. Okay, anyhow, I have shown here certain set of graphs, and please remember these graphs are nothing but experimental graphs. Okay, these experimental graphs are based on experimental results. Okay, and these graphs are nothing but a plot of intensity of radiation against wavelength. Okay, so overall these plots or these graphs represent distribution of energy in the black body spectrum, so given by experiments. Experiment ಮಾಡಾದ್ಮೇಲೆ ಆ ರಿಸಲ್ಟ್ ಏನ್ ಬಂದಿದೆಯೋ ಆ ರಿಸಲ್ಟ್ ಅನ್ನ ನಾವು ಗ್ರಾಫ್ ತರ ಪ್ಲಾಟ್ ಮಾಡ್ಕೊಂಡಿದೀವಿ. ಹಾಗಾಗಿ ಈ ಇಡೀ ಸ್ಪೆಕ್ಟ್ರಮ್ ನ ಅಥವಾ ಇಡೀ ಗ್ರಾಫ್ ಗಳನ್ನ ಏನೇನ್ ಬರ್ತಿದ್ದೀನೋ ಅದನ್ನ ಅನಾಲಿಸಿಸ್ ಮಾಡಿದ್ರೆ, ಅದನ್ನ ಸ್ಟಡಿ ಮಾಡಿದ್ರೆ ನಮಗೆ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಆಫ್ ಎನರ್ಜಿ ಇಂದ ಬ್ಲಾಕ್ ಬಾಡಿ ಸ್ಪೆಕ್ಟ್ರಮ್ ಸಿಕ್ಬಿಡುತ್ತೆ. Okay, now let us try to understand this slowly. So this is a graph. Along y-axis we have taken intensity of radiation, and along x-axis we have taken wavelength. Okay, follow ಮಾಡ್ತಾ ಇದ್ದೀರಾ ಎಲ್ಲಿವರೆಗೂ ಹೇಳಿದ್ ನಾನು?
Yes, sir.
Sir.
Others,
Yes,
please
sir.
unmute yourself and speak.
Yes, sir.
Yes,
Okay.
sir.
Hopefully all of you are following. Okay, and please remember these are the there are some 3 or 4 important results are there. These 3-4 are important results. That is what we are going to discuss. So both classical theory wise as well as quantum theory wise. Okay, so remember distribution of energy in the black body spectrum we are discussing. Basically it is an experimental data we are plotting, in which we are taking intensity of radiation along y-axis and the wavelength along x-axis. Okay, so as you move from origin toward positive x-axis, sorry, positive y-axis, intensity increases. As you move from origin towards the positive x-axis, wavelength also increases. ಅದು ಎಳೆ ಮಕ್ಕಳಿಗೂ ಗೊತ್ತಿರುವಂತ ವಿಷಯ, ನೀವು ತುಂಬಾ ಹಿಂದೆ ಓದ್ಬಿಟ್ಟಿದ್ದೀರಾ. ಸೊ ಯಾವ ಸೆನ್ಸ್ ಅಲ್ಲಿ ವೇವ್ಲೆಂತ್ ಮತ್ತೆ ಇಂಟೆನ್ಸಿಟಿ ರೈಸ್ ಆಗುತ್ತೆ ಅಂತ ನಿಮಗೆ ಗೊತ್ತಿದೆ. ಓಕೆ, and I have shown 3 curves. Okay, 3 distribution curves. The first curve is for the temperature T1, the second curve is for the temperature T2, and the third bigger curve is for the temperature T3. And you should remember that the temperature T3 is greater than T2 greater than T1. Okay, some sort of information ನಿಮಗೆ ಇಲ್ಲೇ ಗೊತ್ತಾಗೋಗ್ಬಿಡುತ್ತೆ. ಟೆಂಪರೇಚರ್ ಆಫ್ ದ ಬ್ಲಾಕ್ ಬಾಡಿ ನೀವು ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಮಾಡ್ತಾ ನಿಮಗೆ ಆ ಬ್ಲಾಕ್ ಬಾಡಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಕರ್ವ್ ಏನ್ ಬರುತ್ತೋ ದೊಡ್ಡ ಸೈಜ್ ಕರ್ವ್ ಬರ್ತಾ ಹೋಗುತ್ತೆ. ನೀವು ಜಾಸ್ತಿ ಟೆಂಪರೇಚರ್ ಇಟ್ರೆ ಅದು ದೊಡ್ಡ ಸೈಜ್ ಕರ್ವ್ ಬರುತ್ತೆ, ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ಇಟ್ರೆ ಚಿಕ್ಕ ಸೈಜ್ ಕರ್ವ್ ಬರುತ್ತೆ. Okay, so this is very clear from the diagram, I think. Okay, so there are 3 curves I have shown at the temperatures T1, T2, T3. The area under the curve T3 is more than compared to the area under the curve T2, and the area under this curve T2, okay, under the curve at the temperature T2 is definitely more than the area covered under the curve, so which is maintained at the temperature T1. So when T3 is greater than T1 greater than, so sorry, T3 greater than T2, T2 greater than T1. Okay, so the very first information that we can infer, ಅಂದ್ರೆ ಈ ಗ್ರಾಫ್ ನೋಡಿದ ತಕ್ಷಣ ಏನು ಗೊತ್ತಾಗುತ್ತೆ ಅಂತಂದ್ರೆ, okay, if you observe any one curve, ಯಾವ್ದಾದ್ರು ಒಂದು ಕರ್ವ್ ಅಬ್ಸರ್ವ್ ಮಾಡಿ, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಟೆಂಪರೇಚರ್ T1 ಅಂತ ಬರೆದಿದ್ದನ್ನೆಲ್ಲ ಅಬ್ಸರ್ವ್ ಮಾಡಿದ್ರೆ ಗೊತ್ತಾಗುತ್ತೆ. Okay, intensity of radiation as a function of wavelength is not constant. Okay, that means energy is not distributed uniformly. Energy is not distributed uniformly. If you observe any one particular curve, this is evident. Okay, so there is no uniform distribution of energy in the black body spectrum. There is a non-uniform distribution of energy in the black body spectrum. Okay, ಆ ಕರ್ವ್ಗಳು ನೋಡಿದ್ರೆ ಗೊತ್ತಾಗುತ್ತೆ ಅವು ಯೂನಿಫಾರ್ಮ್ ಕರ್ವ್ಗಳಲ್ಲ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಫಸ್ಟ್ ಕರ್ವ್ ನೋಡಿ, ಟೆಂಪರೇಚರ್ T1 ನಲ್ಲಿ ಈ ಕಡೆ ಲೆಫ್ಟ್ ಸೈಡ್ ಇಂದ ಶುರು ಮಾಡಿದ್ರೆ ಇಂಟೆನ್ಸಿಟಿ ವೇವ್ಲೆಂತ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇಂಟೆನ್ಸಿಟಿ ಏನಾಗ್ತಾ ಹೋಗುತ್ತೆ, ಇಂಟೆನ್ಸಿಟಿ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಯಾವ್ದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ವೇವ್ಲೆಂತ್, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಅಂತ ಬಂದಿದೆ, ಆ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಅಲ್ಲಿ ಇಂಟೆನ್ಸಿಟಿ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಗುತ್ತೆ. ಆಮೇಲೆ ನೀವು ಲ್ಯಾಂಬ್ಡಾನ ಮತ್ತೆ ಫರ್ದರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದ್ರೆ ಇಂಟೆನ್ಸಿಟಿ ರೈಸ್ ಆಗಲ್ಲ, ಕಡಿಮೆ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. So therefore it is a non-uniform distribution. So the first experimental fact is that there is a non-uniform distribution of energy in the black body spectrum. Otherwise there is no uniform distribution of energy in the black body spectrum. That is one simple experimental fact. Okay, now the second one, so ಅದನ್ನ ಆಗ್ಲೇ ಹೇಳಿದೆ, ಮತ್ತೊಂದು ಸಲ ರಿಪೀಟ್ ಮಾಡ್ತೀನಿ. The second point, an increase in the temperature increases the total energy emitted. Okay, so this total energy is nothing but area under each curve. ಆಗ್ಲೇ ಹೇಳಿದೆ ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಆಗ್ತಾ ಸೈಜ್ ಆಫ್ ದ ಕರ್ವ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದೆ ಅಂತ, ಅಥವಾ ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಆಗ್ತಾ ಏರಿಯಾ ಅಂಡರ್ ಈಚ್ ಕರ್ವ್ ಜಾಸ್ತಿ ಅಂತ. ಓಕೆ, graphically this area actually represents the total energy emitted by the black body. ನೀವು black body ನ heat ಮಾಡ್ಬಿಟ್ಟು ಸೊ ಯಾವುದೋ ಒಂದು particular temperature maintain ಮಾಡಿದಾಗ it is going to emit certain total amount of energy, and the total amount of energy can be graphically found out by the area under each curve. So therefore, so area by the first curve is small, area under the second curve is even larger, area under the third curve is even larger, and as you move from first curve to the second curve to the third curve, you know that the temperature is increasing. So therefore, another experimental fact regarding black body radiation is that with increase in the temperature, okay, of the black body, the total energy emitted by the black body also increases. I hope this is also clear. Okay, so first experimental fact is non-uniformity in the distribution of energy, and the second experimental fact is, okay, it is based on the size of the curve. Okay, so we can say that with increase in the temperature T1 T2 T3 ಅಂತ ರೈಸ್ ಮಾಡ್ತಾ ಹೋದ್ರೆ ಏರಿಯಾ ಜಾಸ್ತಿ ಆಗ್ತಾ ಇದೆ. ಏರಿಯಾ ಜಾಸ್ತಿ ಆಗ್ತಿದೆ ಅಂತಂದ್ರೆ total energy emitted by the black body is also increasing. So therefore, total energy emitted by a black body depends on its temperature, such that more is the temperature of the black body, more is the total amount of energy that is emitted by the black body. Okay, follow ಮಾಡ್ತಾ ಇದ್ದೀರಾ?
Yes, sir.
Yes. Okay, next the third one. So the third one is very simple. ಅದನ್ನು ಕೂಡ ಆಗ್ಲೇ ಹೇಳಿದ್ದೀನಿ. If you observe any one curve, for example T2 curve ನ observe ಮಾಡ್ಕೊಳ್ಳಿ. T2 curve ಇಲ್ಲಿ ಇದೆ, ಯಾವುದೋ ಒಂದು ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಶುರುವಾಗುತ್ತೆ. ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಶುರುವಾದಾಗ ಯಾವುದೋ ಒಂದು ವೇವ್ ಲೆಂತ್ ಅಂತ ತಗೋಣ. ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ವೇವ್ ಲೆಂತ್ ಇಂದ ಶುರು ಮಾಡಿದ್ಮೇಲೆ ನಾವು ರೈಟ್ ಸೈಡ್ ಮೂವ್ ಆದ್ರೆ ಎಕ್ಸ್ ಆಕ್ಸಿಸ್ ಅಲ್ಲಿ ರೈಟ್ ಸೈಡ್ ಮೂವ್ ಆಗ್ತಾ ಹೋದ್ರೆ ವೇವ್ ಲೆಂತ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ವೇವ್ ಲೆಂತ್ ಜಾಸ್ತಿ ಆದ್ರೆ ಇಂಟೆನ್ಸಿಟಿ ಆಫ್ ರೇಡಿಯೇಷನ್ ಕೂಡ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ ಅಲ್ವಾ? ಯಾವುದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ವೇವ್ ಲೆಂತ್, ಅದನ್ನ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಅಂತ ಕರಿತೀವಿ. ಅಟ್ ಪರ್ಟಿಕ್ಯುಲರ್ ವೇವ್ ಲೆಂತ್ ಕಾಲ್ಡ್ ಲ್ಯಾಂಬ್ಡಾ ಎಂ, intensity becomes maximum, it takes a peak, and afterwards with further increase in the wavelength there is a gradual decrease in the intensity. Okay, so that is what the third point I have written. ನಾನು ಅದನ್ನು ಓದಕ್ಕೆ ಹೋಗೋದಿಲ್ಲ, but I will be repeating this again. Okay, for a given temperature the intensity of the emitted radiation by a black body increases with increase in the wavelength, and it becomes maximum at a particular wavelength. It becomes maximum at a particular wavelength, and with further increase in the wavelength, the intensity falls. The intensity of the emitted radiation falls or decreases. Okay, so that is what the third point. Something like ಯಾವುದೋ ಒಂದು particular wavelength ಅಲ್ಲಿ ಆ ಕರ್ವ್ ಪೀಕ್ ಆಗ್ತಾ ಇದೆ, ಹೈಯೆಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ತಗೋತಾ ಇದೆ. ಯಾವ ವ್ಯಾಲ್ಯೂ, ಯಾವ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಅದು ಪೀಕ್ ಆಗ್ತಿದೆ ಅಥವಾ ಹೈಯೆಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ತಗೋತಾ ಇದೆ ಇಂಟೆನ್ಸಿಟಿ, ಆ ವೇವ್ ಲೆಂತ್ ಅನ್ನ ನಾವು ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಅಂತ ತಗೋತಾ ಇದ್ದೀವಿ. Okay, so this is what the third experimental point. Okay, so therefore there is a peaking in the intensity of the radiation for a particular wavelength. Okay, and that is the wavelength lambda m, and this is the third experimental point. Okay, and I think you can also observe this lambda m. ಈ lambda m ನ ನೋಡಿ ಅಥವಾ ಈ ಪೀಕ್ ನ ಅಬ್ಸರ್ವ್ ಮಾಡಿ. So for a temperature T1 lambda m ಇಲ್ಲೆಲ್ಲೋ ಇದೆ. ನಾನೇನ್ ಮಾಡ್ತೀನಿ, ಬ್ಲಾಕ್ ಬಾಡಿ ಟೆಂಪರೇಚರ್ T2 ಅಂತ ರೈಸ್ ಮಾಡ್ತೀನಿ. T2 ಅಂತ ರೈಸ್ ಮಾಡಿದಾಗ lambda m ಏನಾಯ್ತು? ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ T1 ಟೆಂಪರೇಚರ್ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ can somebody
Decrease.
say? Yes, lambda ಏನಾಗಿದೆ? ಕಡಿಮೆ ಆಗಿದೆ ಕಂಪೇರ್ ಟು T1 ಕೇಸ್. T2 ಟೆಂಪರೇಚರ್ ಕೇಸ್ ಅಲ್ಲಿ lambda m ಏನಿತ್ತು ಅದರ ವ್ಯಾಲ್ಯೂ T1 ಟೆಂಪರೇಚರ್ ಕೇಸಿಗೆ ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ lambda m ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಕಡಿಮೆ ಆಗಿದೆ. ಅದೇ ತರ T2 ಇಂದ T3 ಮೂವ್ ಆದ್ರೆ ನೀವು ಅಂದ್ರೆ ಸೆಕೆಂಡ್ ಕರ್ವ್ ಇಂದ ಥರ್ಡ್ ಕರ್ವ್ ಮೂವ್ ಆದ್ರೆ ಥರ್ಡ್ ಕರ್ವ್ ಅಲ್ಲಿ ಅಂದ್ರೆ T3 ಅಂತಿದೆಯಲ್ಲ ಟೆಂಪರೇಚರ್, ಆ ಕರ್ವ್ ಅಲ್ಲೂ ಒಂದು ಪೀಕ್ ಇದೆ, ಆ ಕರ್ವ್ ಅಲ್ಲೂ ಒಂದು lambda m ಬರುತ್ತೆ. ಬಟ್ ಆ lambda m ವ್ಯಾಲ್ಯೂ ಈ ಸೆಕೆಂಡ್ ಕರ್ವ್ ಇದೆಯಲ್ಲ T2 ಅನ್ನೋ ಟೆಂಪರೇಚರ್ ನಲ್ಲಿ ಅದು ಕಂಪೇರ್ ಮಾಡಿದ್ರೆ ಇನ್ನೂ ಕಡಿಮೆ ಆಗ್ತಾ ಇದೆ. Okay, can somebody give some general conclusion? Can somebody give general conclusion?
T3 is greater.
I am talking of lambda m. I am talking of lambda m as a function of temperature. Lambda m peak value ಬರ್ತಿದೆಯಲ್ಲ intensity, ಅದನ್ನ ನಾನು ಏನ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ, ಸೊ ಟೆಂಪರೇಚರ್ ಮೇಲೆ ಹೇಗೆ ಡಿಪೆಂಡ್ ಆಗ್ತಿದೆ ಅಂತ ಮಾತಾಡ್ತಿದ್ದೀನಿ. ಸೊ therefore I want one precise statement, one general conclusion for this particular point.
As temperature increases, wavelength decreases.
Yes, okay, wavelength decreases. Please remember, bari wavelength decreases anta helbardu. As the temperature increases, the wavelength at which the intensity is maximum decreases. ಯಾವ್ದೋ wavelength decrease ಆಗ್ತಾ ಇಲ್ಲ, ಯಾವ wavelength ಗೆ intensity maximum ಇದೆಯೋ ಅದು decrease ಆಗ್ತಾ ಇದೆ. So this is very very crucial, this is very very important. Okay, so with increase in the temperature, the wavelength at which the intensity is maximum decreasing ಅಥವಾ decreases. ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಮಾಡ್ತಾ ಮಾಡ್ತಾ ಈ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಕಡಿಮೆ ಆಗ್ತಾ ಹೋಗುತ್ತೆ ಹಾಗೆ ಹೇಳ್ಬೋದು. ಬಟ್ ಆ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಅನ್ನೋದು ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್. ವಾಟ್ ಇಸ್ ಲ್ಯಾಂಬ್ಡಾ ಎಂ? ಲ್ಯಾಂಬ್ಡಾ ಎಂ is the wavelength at which the intensity is maximum. So therefore we can say that there is an inverse relationship between lambda m and temperature T. ಲ್ಯಾಂಬ್ಡಾ ಮತ್ತೆ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಮತ್ತೆ ಟಿ ಅಂತಿದೆಯಲ್ಲ, ಎರಡಕ್ಕೂ ಇನ್ವರ್ಸ್ ರಿಲೇಶನ್ಶಿಪ್. ಅಂದ್ರೆ ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ಲ್ಯಾಂಬ್ಡಾ ಕಡಿಮೆ ಆಗುತ್ತೆ, ಅಥವಾ ಟೆಂಪರೇಚರ್ ಕಡಿಮೆ ಮಾಡಿದ್ರೆ ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. Okay, so that see, that is what the fourth point. An increase in temperature causes a decrease in lambda m, where lambda m is the wavelength at which intensity is maximum. Okay, such that lambda m t is equal to constant. The product lambda m into t, lambda ಮತ್ತೆ t ನ multiply ಮಾಡ್ಕೊಂಡ್ರೆ constant ಬರುತ್ತೆ. I am extremely sorry, it is not lambda, it is lambda m. Lambda m into t is constant, so that t ಜಾಸ್ತಿ ಇದ್ರೆ lambda m ಕಡಿಮೆ ಆಗುತ್ತೆ, ಅಥವಾ t ಕಡಿಮೆ ಇದ್ರೆ lambda ಜಾಸ್ತಿ ಆಗುತ್ತೆ. Okay, so this product lambda m into t, lambda m is the wavelength at which the intensity is maximum and t is the temperature of the black body. So this product lambda m into t is a constant, and this is what we call it as Wien's displacement law. So our fourth experimental point is that, so Wien's displacement law, according to which the wavelength at which the intensity is becoming maximum, okay, coming out from the black body, actually decreases with increase in the temperature of the black body. Okay na? Okay,
Okay, sir.
okay, shall I
Okay,
continue?
sir.
No doubt in this one.
Yes, sir.
Okay, now as usual I have told that there are 4 experimental facts. All the 4 experimental facts are in this graph.
Yes.
ಈ 4 experimental fact ಹೇಳಿದ್ನಲ್ಲ, ವರ್ಡ್ಸ್ ಅಲ್ಲಾದ್ರೂ ಹೇಳಿ ಅಥವಾ ಚಿತ್ರದಲ್ಲಾದ್ರೂ ಬರ್ಕೊಳ್ಳಿ. ಚಿತ್ರದಲ್ಲೇ ಬರ್ಕೊಂಡಿದ್ವಿ, ಚಿತ್ರದಲ್ಲಿ ಬರ್ದಿರೋದನ್ನ ನಾವು ಇಲ್ಲಿ ಕೆಳಗಡೆ ವರ್ಡ್ಸ್ ಅಲ್ಲಿ ಬರ್ಕೊಂಡಿದ್ವಿ ಅಲ್ವಾ? ಸೊ ಇವಾಗ ಏನು ಪ್ರಶ್ನೆ ಅಂತಂದ್ರೆ, so you should apply a theory. When you apply a theory, and your theory must explain all the experimental facts. These 4 experimental facts ಇದೆಯಲ್ಲ, ಅದನ್ನ ನಿಮ್ಮ theory explain ಮಾಡಬೇಕು. Okay, so therefore classical theory, so we shall discuss classical theories, explanation by classical theories. There are 2 classical, I am mentioning classical theories, it is because there are 2 classical theories. The first one is what we call it as Wien's law, and please remember Wien's law is different from Wien's displacement law. ಈಗ ತಾನೇ Wien's displacement law ಅಂತ ಹೇಳಿದೆ, Wien's displacement law ಬೇರೆ ಮತ್ತೆ Wien's law ಬೇರೆ. Okay, so anyhow there are 2 classical theories to explain the experimental features associated with the energy distribution in the black body spectrum. The first classical theory is what we call it as Wien's law. The second theory is what we call it as Rayleigh-Jeans law. Okay, so these laws are very very difficult to discuss ಮಾಡೋದು ತುಂಬಾನೇ ಕಷ್ಟ, but anyhow we are discussing very very briefly. Okay, so according to Wien's law, or according to Wien, amount of energy dE, follow me carefully. So amount of energy dE in the black body spectrum in the wavelength range lambda to lambda plus d lambda, wavelength na lambda ಇಂದ lambda plus d lambda change ಮಾಡಿದಾಗ, ಅಂದ್ರೆ you are changing the wavelength by an amount d lambda. Okay, so in this wavelength range d lambda, the energy associated with the black body spectrum we are taking it as dE. ಯಾಕೆ ಈ ತರ ಬರ್ಕೋತಾ ಇದೀವಿ ಅಂತಂದ್ರೆ d lambda is very small, so therefore the amount of energy associated in the wavelength range d lambda is also very small. That's why we are writing it as dE. Okay, so therefore the amount of energy dE in the wavelength range d lambda, that is from lambda to lambda plus d lambda at a particular temperature, is given by, Wien ಅನ್ನೋನು ಪ್ರೂವ್ ಮಾಡ್ತಾನೆ ಇದನ್ನ. We shall not worry about the proof and all. ಇದು ಪ್ರೂಫ್ ಮಾಡಕ್ ಆಗಲ್ಲ, ಇದು ತುಂಬಾ ಕಷ್ಟ ಇದೆ. But simply he says, so the energy in the wavelength range d lambda is given by this expression. I have written it as expression 1. Okay, dE is given by k dash lambda to the power of -5 exponential minus a divided by lambda t into d lambda. Okay, where k dash and a are some constants. ಇಲ್ಲಿ k dash ಮತ್ತೆ a ಅಂತ ಬರೆದಿದ್ದೀನಲ್ಲ, ಎರಡು ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗುತ್ತೆ. Lambda, as usual, you know wavelength of the emitted radiation. T is the temperature, and you also know that d lambda. d lambda is the energy, okay, in the, d lambda d is the energy in the wavelength range d lambda. ಈ ಡಿ ಎನರ್ಜಿ ಏನಂತಂದ್ರೆ ವೇವ್ಲೆಂತ್ ರೇಂಜ್ ಡಿ ಲ್ಯಾಂಬ್ಡಾ ರೇಂಜ್ ಒಳಗಡೆ ಎಷ್ಟು ಎನರ್ಜಿ ಇದ್ದದನ್ನ ಡಿ ಅಂತ ಬರ್ಕೊಂಡಿದ್ದೀವಿ. ಓಕೆ, ಸೊ ದಟ್ ಇಸ್ ಯುವರ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ 1. Okay, so therefore this is what we call it as Wien's law. Equation 1 is called Wien's law. You need not have to worry about derivation. Derivation is not possible. It's a very complicated one. But anyhow, Wien proved that. So the energy in the wavelength range d lambda, that is d, is given by expression 1. Okay, where k dash and a are some constants, lambda is the wavelength, t is the temperature of the black body. Okay, so anyhow, so this law, this Wien's law, follow ಮಾಡ್ತಾ ಇದ್ದೀರಾ? Yes, this Wien's law represented by equation 1. The problem with equation 1 is that, say I have written here, Wien's law holds good only in the shorter wavelength region. It does not hold good at longer wavelength region. So ನಿಮ್ಮ ಇಡೀ ಸ್ಪೆಕ್ಟ್ರಮ್ ಏನಿದೆ, ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಶೋ ಸಮ್ವೇರ್ ಹಿಯರ್. ಇಡೀ ಸ್ಪೆಕ್ಟ್ರಮ್ ಏನಿದೆ, ಯಾವ್ದಾದ್ರು ಒಂದು ಸ್ಪೆಕ್ಟ್ರಮ್ ತಗೊಳ್ಳಿ, ಒಂದು ಕರ್ವ್ ತಗೊಳ್ಳಿ. ಒಂದು ಕರ್ವ್ ಅಲ್ಲಿ ನೀವು ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಈ ಕರ್ವ್ ನ ಇದನ್ನ ಲ್ಯಾಂಬ್ಡಾ ಎಂಬ ಮಿಡ್ ಪಾಯಿಂಟ್ ಅಂತ ತಗೊಂಡ್ರೆ, ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಗಿಂತ ಕಡಿಮೆ ಇರೋದನ್ನ ಶಾರ್ಟರ್ ವೇವ್ಲೆಂತ್ ರೀಜನ್ ಅಂತ ಕರಿತೀವಿ. ಲ್ಯಾಂಬ್ಡಾ ಎಂ ಗಿಂತ ಜಾಸ್ತಿ ಇರೋದನ್ನ ಲಾಂಗರ್ ವೇವ್ಲೆಂತ್ ರೀಜನ್ ಅಂತ ಕರಿತೀವಿ. ಪ್ಲೀಸ್ ರಿಮೆಂಬರ್, ಅಕಾರ್ಡಿಂಗ್ ಟು ಅವರ್ ಕನ್ವೀನಿಯನ್ಸ್, the wavelength region along x-axis can be splitted into two parts. One is what we call it as longer wavelength region, higher wavelength region, athwa longer wavelength region. Another side, the opposite side, is what we call it as shorter wavelength region. ಎಲ್ಲೆಲ್ಲಿ wavelength ಕಡಿಮೆ ಇರುತ್ತೋ ಅದನ್ನ shorter wavelength region ಅಂತ ಕರಿತೀವಿ. ಎಲ್ಲೆಲ್ಲಿ wavelength ಜಾಸ್ತಿ ಇರುತ್ತೋ ಅದನ್ನ longer wavelength region ಅಂತ ಕರಿತೀವಿ. Okay, now you come back here. The problem with Wien's law is that, so Wien's law could give proper explanation only in the shorter wavelength region or regions, whereas it failed to give proper explanation in the longer wavelength region. So therefore, I want to conclude. We are not discussing this, although we are not discussing in detail. We cannot discuss this one in detail. Of course, this is only this much is sufficient for you people. Just I want to say that equation 1, which actually represents your Wien's law, holds good only in the shorter wavelength region. It does not hold good in the longer wavelength region. Shorter wavelength region nan matra successful agi explain ಮಾಡುತ್ತೆ Wien's law. Adre longer, Amir ಏನು ಬರೀತಿದ್ಯಪ್ಪ, Amir you are writing something. Okay, in the higher wavelength region, okay, so it does not give proper explanation. There is no explanation by the distribution, there is no explanation for the distribution of energy in the longer wavelength region by Wien's law, but it could explain distribution of energy only in the shorter wavelength region. So therefore, the theory Wien's law was discarded. Why it was discarded? The classical theory called Wien's law was discarded. Why it was discarded? Because it could not explain the complete spectrum. It could explain only partially, only at shorter wavelengths. It could not explain at the longer wavelengths. Okay, so therefore, this Wien's law fails to give proper explanation to the distribution of energy in the black body. Howda? Shall I conclude about Wien's law in this way?
Yes.
Others?
Yes, sir.
Yes, sir.
So we can conclude one classical theory called Wien's law failed to explain distribution of energy. Okay, although it could explain in the shorter wavelength, it could not explain in the longer wavelength. Okay, short wavelength region alli successful agi explain madidru, higher wavelength ಅಥವಾ longer wavelength side ಅಲ್ಲಿ ಈ ಥಿಯರಿ ಫೇಲ್ ಆಯ್ತು. ಯಾವುದೇ ಒಂದು ಜಾಗದಲ್ಲಿ ಫೇಲ್ ಆದ್ರೂ ಕೂಡ ನಿಮ್ಮ ಥಿಯರಿ ಫೇಲ್ ಆದಾಗ ಲೆಕ್ಕ. ಹಾಗಾಗಿ ನೀವು ಆ ಥಿಯರಿನ ಕೈ ಬಿಟ್ಬಿಟ್ಟು ಮುಂದಕ್ಕೆ ಹೋಗ್ಬೇಕು. So therefore, Wien's law we have to avoid, or we have to discard, and we have to go for the next one. The next classical theory is what we call it as Rayleigh-Jean's law. Okay, the next theory is what we call it as Rayleigh-Jean's law. So two persons called Rayleigh and Jean together, they proposed one more law. Okay, that is what we call it as Rayleigh-Jean's law. And just like your Wien's law, derivation of Rayleigh-Jean's law is difficult. Okay, so just a second. Okay,
Sorry, sir.
okay, so Rayleigh and Jean proposed another law. Okay, again mathematically it is a complicated law. Again we should not bother about this derivation. So simply we shall use the derivation. Rayleigh and Jean Prove that energy D in the wavelength range lambda to D plus lambda to lambda plus D lambda is given by same previous case ಅಲ್ಲಿ discuss ಮಾಡಿದ್ರು same ಅದೇ ಬರುತ್ತೆ. D is equal to 8 pi divided by lambda power 4 K into T into D lambda. Okay, so this is equation 2. So equation 2 represents Rayleigh-Jeans law. Okay, so 8 and pi are constants. Lambda is wavelength, you know that one. T is the temperature, and K is your Boltzmann's constant. K and n bardidino, this is your Boltzmann constant. Okay, and you can say that equation 2 is different from equation 1. So now observe madi, equation 1 ne bere formula ide, equation 2 ne bere formula ide. Okay, although both of them are classical theories, but definitely both the theories are different theories. Okay, that's why we are getting two different mathematical function. Here this is exponential function, here there is no exponential function, but still we have 1 by lambda to the power of 4 anta ide. So therefore this is another classical theory. Okay, again the problem with this Rayleigh-Jeans law is that this law holds good only at longer wavelengths. Okay, so and it fails to give proper explanation of for energy at shorter wavelengths. ಇದು ನೋಡಿ, ಇದು ರಿವರ್ಸ್ ಕೇಸ್. ಇದು ಏನಾಗ್ತಾ ಇದೆ ಅಂತಂದ್ರೆ Rayleigh-Jeans law ಏನಾಗ್ತಿದೆ ಅಂತಂದ್ರೆ, so this Rayleigh-Jeans law holds good only at longer wavelengths but fails to explain the energy at shorter wavelengths. So we have something like a problem, exactly opposite problem of that of the Wien's law. Wien's law properly explains the distribution of energy at shorter wavelengths, but it fails to explain at longer wavelengths. And your Rayleigh-Jeans law is such that it is not able to give proper explanation at shorter wavelengths, but it gives a good explanation at longer wavelengths. So therefore again there is a problem here. There is a problem associated with Rayleigh-Jeans law. There was a problem associated with Wien's law. So the same problem is continuing in Rayleigh-Jeans law, but of course in a slightly different form, in just opposite form, such that so Rayleigh-Jeans law explains the distribution of energy at longer wavelengths, but it fails to give explanation at shorter wavelengths. So therefore the conclusion is Rayleigh-Jeans law, another classical theory, also failed to give proper explanation for the distribution of energy in the black-body spectrum. So therefore we can conclude, follow ಮಾಡಿದ್ರಲ್ಲ, ಗೊತ್ತಾಗ್ತಿದೆಯಲ್ಲ, Rayleigh-Jeans law ಮತ್ತೆ Wien's law ಎರಡು ಆಪೋಸಿಟ್. Wien's law ಲೋಯರ್ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಸಕ್ಸಸ್ಫುಲ್ ಆಗಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದ್ರೆ Rayleigh-Jeans law ಲೋಯರ್ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಫೇಲ್ ಆಗುತ್ತೆ. Wien's law ಹೈಯರ್ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಫೇಲ್ ಆದ್ರೆ Rayleigh-Jeans law ಹೈಯರ್ ವೇವ್ ಲೆಂತ್ ಅಲ್ಲಿ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಕೊಡುತ್ತೆ. ಬಟ್ ಎಲ್ಲರೂ ಕೂಡ ಪಾರ್ಷಿಯಲ್ ಥಿಯರೀಸ್ ಆಗೋಯ್ತು. ಒಂದೊಂದು ರೀಜನಲ್ ವರ್ಕ್ ಆಗ್ತಿದೆ, ಇನ್ನೊಂದು ರೀಜನಲ್ ವರ್ಕ್ ಆಗ್ತಿದೆ. Wien's law is not working at higher wavelength regions. Okay, whereas your Rayleigh's law, your Rayleigh-Jeans law is not working at shorter wavelength regions. So therefore both the theories have shortcomings and both the theories are improper. So therefore both the theories are incomplete. Okay, so therefore we have to reject both the theories. Okay, so that's why classical theories, conclusion I have written here, both Wien's law and Rayleigh-Jeans law could not explain the distribution of energy of a black body. Okay, because both of the theories are based on the continuous emission and absorption of radiation. Okay, the problem with both the theories was that ಎರಡರಲ್ಲೂ ಯಾಕೆ ಪ್ರಾಬ್ಲಮ್ ಆಯ್ತು ಅಂತಂದ್ರೆ, both the theories are based on the concept that emission of radiation and the absorption of radiation happens in a continuous fashion. So that's why both the theories failed. Okay, so the problem with both the theories was that ಎರಡರಲ್ಲೂ ಒಂದೇ ಕಾಮನ್ ಪ್ರಾಬ್ಲಮ್ ಇತ್ತು. ಆ ಕಾಮನ್ ಪ್ರಾಬ್ಲಮ್ ಏನಂತಂದ್ರೆ, ಎರಡು ಬೇರೆ ಬೇರೆ ಥಿಯರಿ, ಕ್ಲಾಸಿಕಲ್ ಥಿಯರಿ ಆದ್ರೂ ಕೂಡ ಎರಡರಲ್ಲೂ ಒಂದೇ ಕಾಮನ್ ಪ್ರಾಬ್ಲಮ್ ಇತ್ತು. ಎರಡರಲ್ಲೂ ಒಂದೇ ಒಂದು ಕಾಮನ್ ಫೌಂಡೇಶನ್ ಇತ್ತು. ಆ ಕಾಮನ್ ಫೌಂಡೇಶನ್ ಏನಂತಂದ್ರೆ, Rayleigh-Jeans law ಮತ್ತೆ Wien's law ಎರಡು ಕೂಡ, if there is an emission of radiation or if there is an absorption of radiation, and that emission or absorption happens in a continuous manner. So that is what the foundation principle, and because of this fundamental foundation principle, continuous emission or continuous absorption, both the theories failed. Okay, are you following?
Yes, sir.
I hope you are following. So can somebody say what was the problem with both the theories? ಎರಡು ಥಿಯರಿಗಳು ಯಾಕೆ ಫೇಲ್ ಆದ್ರು ಅಂತ ಯಾರಾದ್ರೂ ಒಂದು ಬೇಗ ಸಮರೈಸ್ ಮಾಡಿ ಹೇಳ್ತೀರಾ ಒಂದೇ ಲೈನ್ ಅಲ್ಲಿ?
Sir,
can somebody say what was the common problem associated with both the classical theories, Wien's law and Rayleigh-Jeans law? Quickly, I don't have time.
Rayleigh-Jeans law could not explain about
No. I don't want that explanation. Lower wavelength, higher wavelength, that I don't want. Somewhere they failed. Wien's law failed at some point, Rayleigh-Jeans law failed at some point. Both of them failed at some point. It is basically because both of them assume, both the theories assume that absorption and emission takes place in a continuous fashion. This was the problem. Okay, so this was the problem because of continuous emission or continuous absorption ಅಂತ assume ಮಾಡ್ಕೊಂಡಿದ್ರಿಂದ both the theories failed to give proper explanation. Okay, anyhow, I'm just continuing in the same fashion. Max Planck in the year 1900 identified this problem. Max Planck ಈ ಪ್ರಾಬ್ಲಮ್ ನ ಸ್ಟಡಿ ಮಾಡ್ತಾ ಇದ್ದ, ಯಾಕೆ ಕ್ಲಾಸಿಕಲ್ ಥಿಯರಿ ಎರಡು ಫೇಲ್ ಮಾಡೋದು ಅಂತ. ಅವಾಗ ಅವನಿಗೆ ಗೊತ್ತಾಯ್ತು ಯಾಕೆ ಎರಡು ಥಿಯರಿಗಳು ಫೇಲ್ ಆಗ್ತಿದೆ ಅಂತಂದ್ರೆ both the theories assume that emission and absorption happening in continuous fashion. ಆ ಐಡಿಯಾದಿಂದನೇ ಪ್ರಾಬ್ಲಮ್ ಆಗ್ತಿದೆ ಅಂತ ಅವನಿಗೆ ಗೊತ್ತಾಯ್ತು. So therefore he discarded that continuous emission or continuous absorption. Max Planck in the year 1900 told that absorption of radiation or emission of radiation do not take place in a continuous fashion, but absorption and emissions take place in discrete packets of energy, or he called it as quantum. If there is an emission, the emission does not happen in a continuous way. The emission happens in small packets of energy called quantum or quanta. In a similar way, he told that if there is an absorption of radiation does not happen in a continuous fashion, but absorption happens in terms of small packets of energy, quantum. ಒಂದಾದ್ರೆ quantum, ಒಂದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಇದ್ರೆ quanta. Okay, so that's why this theory is what we call it as Planck's quantum theory. Okay, he introduced this quantum concept. What is the quantum concept? Emission or absorption, they are not continuous, they are discrete. They are discrete and they happen in small packets of energy, and each packet of energy was given the name quantum. Okay, so actually now ಇದನ್ನ ಇದಿದೆಯಲ್ಲ ಯಾವುದು Planck's quantum theory ನ ಫಸ್ಟ್ ಡಿಸ್ಕಸ್ ಮಾಡಿ ಉಳಿದಿದ್ದೆಲ್ಲ ಆಮೇಲೆ ಡಿಸ್ಕಸ್ ಮಾಡಬೇಕಾಗಿತ್ತು. ಬಟ್ ಏನೇ ನೋ ಪ್ರಾಬ್ಲಮ್. ಓಕೆ, ಯಾಕಂದ್ರೆ Planck's quantum theory ಇಂದನೇ ಬೇರೆ ಎಲ್ಲಾ ಥಿಯರಿ ಕೂಡ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬಹುದು. ನಾನು ಹಿಂದೆ ಮೊನ್ನೆ ಎಲ್ಲ ಏನೇನು ಕ್ಲಾಸಸ್ ಮಾಡಿದ್ದೆ ಆ ಕ್ಲಾಸಸ್ ಅಲ್ಲಿ ಬರೋ ಪ್ರತಿಯೊಂದನ್ನು ಕೂಡ ಸೊ ವಿ ಕ್ಯಾನ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಆನ್ ದ ಬೇಸಿಸ್ ಆಫ್ ಕ್ವಾಂಟಮ್ ಥಿಯರಿ. ಹಾಗಾಗಿ ಫಸ್ಟ್ ಕ್ವಾಂಟಮ್ ಥಿಯರಿ ಡಿಸ್ಕಸ್ ಮಾಡಬೇಕಿತ್ತು. But no problem, I'm discussing now. So therefore I can say that based on this quantum picture which says that emission and absorptions happen in packets of energy, and each packet of energy is given the name quantum. That's why the theory is called quantum theory. And just I would like to say, based on the quantum theory, Planck successfully explained the distribution of energy in the black body spectrum, and that is what we are discussing now. Okay, any doubt? Another doubt idre keli. Follow ಮಾಡ್ತಾ ಇದ್ದೀರಾ?
Yes sir.
Hopefully others are also following. Okay, and he says energy of each quantum is h nu. That all you know. Okay, energy of each quantum is h nu. Okay, where h is Planck's constant and nu is nothing but the frequency of the radiation. Okay, so therefore he says a packets of energy anta helidvalla, each packet has an energy of h nu, where h is Planck's constant, some constant, we call it as Planck's constant, and the nu is nothing but your so frequency. A photon athwa quantum ತಗೊಂಡಿರಲ್ಲ ಅದು ರೇಡಿಯೇಷನ್ ಅಂತ ಯಾವುದು ತಗೊಂಡಿದ್ರೆ ಅದು ರೇಡಿಯೇಷನ್ ದ ಫ್ರೀಕ್ವೆನ್ಸಿ. Okay, so I have already told, based on this Planck explained the distribution of energy in the black body spectrum. Okay, there are two postulates. Okay, I'm going to explain the two postulates in 2 ನಿಮಿಷ ಇದೆ. ಈಗ ಆದ ತಕ್ಷಣ ಮತ್ತೆ ಕೂಡ ಇನ್ನೊಂದು ಮೀಟಿಂಗ್ ಸೆಟ್ ಮಾಡ್ತೀನಿ, ಒಂದು 10-15 ನಿಮಿಷ ಟೈಮ್ ಆದ್ಮೇಲೆ. ಓಕೆ, ಅವಾಗ ಇನ್ನೊಂದು ಮೋಸ್ಟ್ಲಿ ಒಂದು 20 ಅಥವಾ 25 ನಿಮಿಷದಲ್ಲಿ ಕಂಪ್ಲೀಟ್ ಆಗುತ್ತೆ ಅಂತ ಅನ್ಸುತ್ತೆ. But anyhow, in just 2 minutes of time, I am going to explain the Planck's postulates. The two postulates are very simple. I have already told a black body contains oscillators. I have not told actually. A black body contains oscillators of atomic dimension, and these atomic oscillators would be oscillating. Okay, when these atomic oscillators are oscillating with the frequency nu, actually they can actually vibrate with all possible frequencies. Okay, so an oscillator of frequency nu can have discrete value of energy given by your quantum theory is equal to h nu, where n can be either 0, 1, 2, 3, etc., etc., and h is Planck's constant. Okay, I want to repeat. So a black body would be consisting of oscillators of atomic dimension. They are called atomic oscillators, and the atomic oscillators, they would be oscillating with the frequency nu, and that frequency can actually change from 0 to infinity. Okay, so that means your atomic oscillators can can actually vibrate with all possible frequencies. So that is what the one thing. And the energy associated with these oscillators is given by nh nu, where n can be either 0, 1, 2, 3, etc. Okay, you know that that is actually what we call it as some quantum number, and h is Planck's constant. Okay, and this atomic oscillator can emit or absorb energy in discrete set of energies in h. Okay, this atomic oscillator either it can emit or it can absorb. Emit ಮಾಡಿದ್ರೆ ಅಥವಾ ಅಬ್ಸರ್ವ್ ಮಾಡಿದ್ರೆ ಯಾವಾಗಲೂ ಕೂಡ ಸೊ NH nu ಮಾತ್ರ ತಗೊಳುತ್ತೆ. ಓಕೆ, ಸೊ ಇಲ್ಲಿಗೆ ಮೀಟಿಂಗ್ ಎಂಡ್ ಮಾಡ್ತೀನಿ ಅಥವಾ ಮುಗಿಯುತ್ತೆ ಈಗಲೇನೆ. ಸೊ ಇನ್ನೊಂದು ಮೀಟಿಂಗ್ ನ ಸೆಟ್ ಮಾಡಿ ನಾನು ನಿಮಗೆ ಕಳಿಸ್ತೀನಿ. ಓಕೆ.